Oh, thank you, Kat. You must have done that.
Nope.
Oh, maybe I told it to do it automatically, like I did for everything else. Well, welcome everyone, and we'll get started here in just a couple minutes. We'll let a few more people filter in. Um, we are also live streaming this on YouTube, and so the general public will also be able to see this. Those of you that are here on the Zoom feed, you'll be able to interact with each other. Feel free to greet each other in the chat and let us know where you are. If you happen to have any questions, please use the Q&A window. That way, any of your conversations in chat, your questions won't get lost. So please go ahead and put any questions in the Q&A window. That way we can keep track of them. And I'm going to go ahead and turn it over to Greg, and he'll introduce Kelly. So, Greg.
All right. Welcome, everyone, to tonight's evening event, public science talk from a leading heliophysicist, Kelly Korreck from NASA headquarters. So take it away, Kelly.
Great. Thank you so much for having me. I am so happy to be talking about NASA's mission to touch the sun, Parker Solar Probe. So I worked on Parker Solar Probe for over 10 years, developing one of the instrument suites aboard this once in a lifetime mission. And I'm really excited to share a little bit more about the sun. We had all that excitement with the eclipse this year and last year, the annular eclipse in 2023. And then with the solar storms in 2024, in May of this year, that we got to see aurora all over. There's so much to learn and so much that Parker is really helping us understand about this. Our closest star, the sun. So the sun that we think of, and again, we all know not to look up at the sun without eye protection. But if you were able to take a safe image, you would see something like this. Now it would actually probably have more of those dark and white spots on it. And when we zoom in, we see that those are sunspots. So most of us know that sunspots are around and that they're magnetic. And the sun, it goes through cycles where it has a few of them and then has very, very little of them. And that's around 11 years that the cycle takes. And it has to do with a magnetic pole reversal. And this has been known for quite some time. This is a 11th century depiction of what would be sunspots on the sun, observing the sun in Korea. Then we also have beautiful drawings of the sun. This is one from Langley, who was at the time at the Smithsonian and had actually used a viewer to draw this into the exquisite detail, these little tendrils going into the magnetic field and just a typical sunspot. But again, you can see so much detail, so much going on. You could almost feel it moving and seething. And that's really what the corona does. It kind of comes alive. And it's that part that reaches out from the sun towards us. But nowadays we have beautiful images such as this from the Solar Dynamics Observatory. And we're watching this. All of these would have little sunspots under them, these active regions. They're intense magnetic activity in those regions. And those are the birthplace of things such as coronal mass ejections, which is equivalent to around 80 million school buses being released at 1,000,000 miles an hour heading out towards into the solar system. This also can create a lot of energetic particles, and those energetic particles can interact with our power grids, with our satellites, and really cause some havoc when they're not, when we don't know that they're coming. This can also provide the energy and particles that help us see the beautiful aurora way down, even to the south during these high activity times. So again, I was talking before about it's a very active star, even though it looks kind of gentle in our day sky when we're lucky enough to have it out in the day. It really is very complex and really scientifically interesting to boot. And again, referencing back to the eclipses, this is a 2008 picture actually of an eclipse. And at Parker, at closest approach, Parker would be seen in the eclipse. So 9.86 solar radii is the closest approach, which we will reach on December 24th of this year. But also, in addition to seeing eclipses, we can now make modern eclipses with to better study our sun and to be able to understand what's going on. And so Parker is going into these things, but it's also important to have these other observation points to really understand what's going on at Parker. So on the left, you see an image that has been processed such that you add up enough images to see the outer corona and all of its structures. You see some loop structures. You might see some things flowing outward, streamers or wind streams. And you see some even strange stripes kind of up in the upper right corner, some like U shapes. There's a lot of complexity here to understand how our magnetic star works. And then over here on the right, you actually see a coronagraph where we've blocked out the sun. So the occulter, the white circle is the size of the sun. And since our spacecraft still are not quite as good as our moon, our occulter has to be bigger so that they're stable enough to really block out the sun. And then you can see these wispy stripes coming out, the solar wind, or this constant wind and outflow that is flowing out of the star. The white dots you see in the background are actually stars, other stars, and then it's probably a planet that's so bright in that artificial eclipse. So having that play as a movie, we actually see like a ring puff go off this way, different large explosions to the upper left and the lower right show us that our star is really active. One just went off to the upper right as well. And this is about what it's doing these days. The sun is very active, throwing off all these particles, and Parker is really right in the middle of it. And this is one of the main reasons why we wanted to send Parker so close. All right. While it loads. So Parker, again, there we go. And one of those reasons is really space weather. So as the sun produces this weather, it can send off those particles that, again, damage spacecraft electronics. Solar flare protons can, again, damage electronics and cause even issues for radiation effects on avionics or on our flights. There are issues with the ionosphere. The ionosphere, or the layer of the atmosphere that's charged, will basically collapse at times, and so we can't send communication signals that we normally do. So it's really important to understand and be able to predict when these things are happening. We can safeguard against all of them. It's just a matter of understanding that, and Parker plays a role in doing all of that. So again, the drivers of space weather, it's the flares, and that's the magnetic explosion. So the magnetic loops we saw in the first few slides that were twisting and actually reorganizing catastrophically have a big explosion and a bright white light, and that is the solar flares. Coronal mass ejections, like I said before, was the 80 million school buses at millions of miles an hour. And then the energetic particles are just those particles that are thrown off fastest, closer to the speed of light than the rest of them. And so they arrive a little bit earlier to interact with our magnetosphere, our protective magnetic bubble, as well as the Earth's atmosphere in general. So the other reason why we're interested in kind of this scale is pure plasma physics, besides the space weather, plasma physics. So if you're looking at the ratio of the sun to the Earth and 1 AU, the distance that we use between the two, is the fact that Parker Solar Probe goes to less than 0.1 AU allows us to go to the transition from collisions to collisionless plasma, which means that we're used to living in collisional plasma. We get warm because we have thermal conduction in the air, and that's one of the reasons why we can kind of stay warm. Well, when you're in collisionless plasma, you can't transfer heat like that. So we are going into the collisionless regime when we go to Parker's, and that is one of the areas of study and what makes Parker a great plasma laboratory. And again, this is not to scale. The other reason is this Alfvén point. We wanted to go past the Alfvén point and transition from the atmosphere of a star to the stellar wind. So closer to the sun from the Alfvén point, it's the atmosphere of the star. And then the stellar wind is after this Alfvén point. This Alfvén point, it's not just a point, it's actually a surface, because it's the balance between where the sun can keep all of its atmosphere and where it's actually starting to push it away and then accelerate it. And the design of Parker Solar Probe was to go within that point and make sure that we were making measurements of the actual atmosphere of the star and not just the stellar wind, because we have had measurements for a while now of the stellar winds that are outside. We have never been this close, and there is a lot of processing when you go between 0.1 and 1 AU, but we definitely wanted to go in and make sure that there was some time inside the actual atmosphere of the sun, since we went through all the trouble of going there. And just to, again, give you a sense of scale and that 1 AU scale, this is about a quarter of the sun and one of those large prominences that could explode or jump off or be thrown off the sun. And this is the approximate size of the Earth. So we are very small compared to all of these effects, but it can affect us in big ways. So Parker Solar Probe was 60 years in the making. And the goal was to determine the structure and dynamics of the sun's coronal magnetic field, which we looked at through those, again, loops and the movies, as well as the sunspots. So we wanted to understand all of that, understand how the solar corona and wind are heated and accelerated as they go and leave the Alfvén surface, and determine what mechanisms actually accelerate and transport those energetic particles that come racing towards us. This is a common in all of astronomy, but specifically to us, kind of more importantly for the space weather, how these are accelerated, so we understand how to prepare ourselves. And there are three reasons why we're going. And first of all, we are explorers, so we want to make sure that we're exploring all bits of the solar system. There's a practical matter of living with that star and its space weather, and then scientific curiosity. So, the very formal definitions were, NASA does a lot of, requirements. And so requirements and objectives are what the first statement was. And the second statement is more about why we're doing this. And besides that, we're doing this because the Simpson Committee of the Space Science Board, which also was the one to actually found NASA, was the one who first directed us to go to the sun. It directed us to visit all of the then 9 planets, and we've done those with various missions for NASA and visit the star. So when we completed Parker Solar Probe, we completed the work there. And the scientific curiosity piece is really interesting because I think that the sun is really mysterious, and it does at least 2 really weird things that we're trying to figure out, and we'll talk about those as we go along. So looking at the first objective that we laid out, it was to trace the flow of energy that heats and accelerates the solar corona and solar wind. So you're looking at 174 angstroms, or 17.4 nanometer pictures. So in the extreme ultraviolet extreme ultraviolet, and you see a lot of hot plasma around there. And one of these scientific curiosities is the fact that the heating, it goes on in the center of the core, the energy generation and the fusion. You get to the photosphere, that yellow ball, it's 5,800 degrees, and now you're seeing pictures of things that are over 1 million degrees. So how did you walk away from that campfire that's in the middle making all the energy, and you actually got warmer? So this is, again, tracing that energy that goes to kind of cooler, then warmer, then cooler again. How does that happen? Where is that energy generation happening for all of this beautiful activity in the solar corona? So again, tracing that flow, we're looking at how the magnetic energy is converted into heating both the ions and electrons, the main stuff that makes up the solar wind. And how does the thermal and kinetic energy of the plasma change with distance? You're seeing a vision or a visual of the SDO-AIA imaging running through different wavelengths. So again, the photosphere, which is cooler, to the hotter atmosphere. And how do we trace, again, that energy? How does it flow? That's what most of physics is about, is where does the energy flow? How does it change? And then below that, you see Hinode XRT, you start to see these jets that come away from the sun. So how are we creating those hot jets that leave the sun? The other images are suggestions as to what mechanisms might actually be doing that. There's wave turbulence, as well as magnetic reconnection, or a reorganization of the magnetic field that could be contributing to this. And Parker is working on that. Parker's second objective was to determine the structure and dynamics of plasma and magnetic fields as at the source of the solar wind. So we saw this image earlier where the sun is occulted with a disk from the SOHO satellite, LASCO instrument. The sun is the size of the white circle in the middle. The outflows you're seeing are a combination of solar wind, as well as coronal mass ejections and streamers. So we wanted to determine that the magnetic fields there at the surface. Here we go. I apologize. It's the movie is loading. My cat put my there we go. There we go. Let's go back one. Okay, so yeah, so looking at the magnetic structure and dynamics of the plasma and the magnetic fields. So these are somewhat images that only a scientist could love, and really I'll show in some later slides kind of the translations that are happening with Parker from these things that in some ways only a scientist could love, to something that is much more visual and much more kind of understandable in general. So we see on the left these images of the sun, and then you see squiggly lines coming out from them. And that has to do with the closed or openness of the loop. So whether the loops of the magnetic field come back to the sun or whether they're just splayed outward. And the first orbit of Ulysses, things were pretty orderly and calm. They become chaotic after a while, and so you see mixtures of open and closed field lines, and then again a little more structured at the third orbit. And this tells you, as the sun becomes more active, what the magnetic structure is of the sun. You see in the top right an image of an eclipsed sun, where you again see all this magnetic structure, and then models on the bottom of this closed and open field line. This is important because it tells you where the flow of the solar wind might come. If something's closed, as you can imagine, things aren't really escaping from that region, so they're not coming towards you. Whereas those that are open, that's where you expect a fast wind, something to come towards you very quickly. So it's, again, important to understand for space weather, as well as understanding the structure of our star. So the third objective for Parker was to explore the mechanism that accelerates and transports energetic particles. So it was also looking at the roles of shocks, reconnection, waves, turbulence in the acceleration of energetic particles. So this picture or the movie that's playing behind the words has a flare go off in a failed CME, where the mass is being ejected, but there are particles that are accelerated during this. And you might imagine seeing some of them. This is a bright light will be some of the acceleration, but there's also some stuff slipping off here. And so we're looking at the source populations as well that are needed to actually make things energetic. So basically looking at that flashing region before it becomes the flashing region and understanding what type of particles are there and how they will be accelerated through the heliosphere. So let's take a look at the spacecraft and the instrumentation that we sent to study the sun. So this is the payload, and in the right hand, the most rightmost image is Parker in the fairing on top of the rocket, and she's ready to go on her voyage. And you'll see the flat top that is a 4-inch carbon-carbon shield. That is what keeps us cool, as well as the struts that you see below it is actually water-cooled radiators that allow the heat to dissipate. So that actually on the back end at closest approach, we actually need a heater because you've blocked out all the light from the one energy source that you have when you're that close to the sun. And we have these beautiful little flexi solar panels. You can also see them in the middle and the far left. They tilt at the bottom so that they can just put out their little fingertips so it doesn't get too hot. And then when we're far away from the sun, they can fully extend so they can get all of the energy that they need to continue to power the spacecraft. There are 4 electric field antennas that go out in front, because that was one of our objectives, is to really understand the electric and magnetic fields. So the magnetometer hangs off the back to get magnetic field measurements that we're flying through. There's a low and high energy solar particle detector and to get those energetic particles. There's a white light imager to take pictures, as well as, again, the cooling arrays are up just past that, and the high gain antenna because it has to phone home and tell us all about the data. So the white light imager is named Whisper. The sweep instrument suite, which I was a part of, is the solar probe cup, which sticks out around the heat shield, and span A and span B. So one A is ahead and B is behind, so that you can look in both directions. So you see both in front of you and behind you, and are able to tell what the particles are coming at you from any direction. You saw the fields antennas, and ESIS is the epi-high and epi-low measurement of high energy particles. So looking at the measurements that are needed to meet those objectives, and we were talking about tracing the flow of energy that heats the corona and accelerates the solar wind. This is a plot of the height above the photosphere, so that yellow ball that we see in the sky, versus temperature. And again, you see the temperature goes up as we go from the chromosphere out to the corona, and then beyond, the solar wind heats up initially and then falls in temperature. So we're looking at radiation, solar wind, we're looking at thermal conduction back and forth, both inward and outward. And these are all the measurements that we need to take in order to understand where things are flowing. And just this year in Science, they have actually started publishing the temperatures of the observed from the corona, plus the measurements that Solar Probe and Solar Orbiter are taking together. So Parker is taking these measurements, Solar Orbiter these, and since they were aligned, we're able to start to put together that map and fill that in more instead of with remote observations, with actual observations from spacecraft. So as we get more time and as we go around more into these areas, we're able to start tracing that flow. So the fields measurements we needed is because they hint at what the heating mechanisms actually are of both the corona and the solar wind. And so here, again, plots that scientists love. It's talking about what the helium does, which is a part of the solar wind, as well as hydrogen or protons. and electrons, and who is actually carrying all the energy around. That's why we need our magnetic field measurements. And our ESIS particle suite, they're again produced in the flaring regions. They're hazardous to our space assets, and so they're also generally interesting. This is also known as some of the snow that you see in some of the solar images. When an energetic particle event goes by one of our cameras, it will pixelate it. And these are actual hits from an energetic particle, not a data point. So we do experience those in our data, and we do see them and work to understand them better. So WHISPER, our white light imager that we have on board, took these images in the background of streamers, so things streaming off the sun. And the high structure that we've only seen from far away can now actually be imaged up close. So over an encounter or one loop around the sun, we're able to determine large-scale structures like these and produce density profiles. So we know how thick the stuff is that we're running through. And we have a high time resolution to study variable structures near the spacecraft. So if a shock from a coronal mass ejection is passing by, or a co-rotating interaction region where two things catch up to each other and cause a shock, streamers, reconnection, turbulence, we can see that all in addition to measuring it. And I think this is a great complement to some of those squiggly line plots, like even seen down here, that we use as scientists. So again, we're looking at these measurements and trying to make things that a scientist loves and knows, and thinking about it in different ways. So in situ, when we think about solar wind, these are traditional plots about the velocity and how much, so you can think of each circle as how much of the stuff that's there has that speed. And as it goes out, there's kind of less and less things, and kind of where things lie. Then we go here, and this is a remote sensing. So something sitting at Earth looking at the sun, how do we measure? We have to actually know a little bit about spectra, atomic spectrum, and wavelengths and counts, and how much then density we have inside this curve. So there's a lot of different ways we're doing it. And that's much like on Parker Solar Probe, where we have a sweep Parker Solar Probe, which actually on Parker Solar Probe measures things such as the in situ. We have remote sensing here on Earth, and we also have WHISPER helping us with some of the electron measurements. And these are some of the things that we're seeing remotely as well. And so we have to figure out how to translate this image into something like this, and vice versa, and make sure that all the data together is really hanging together so that we're getting the right answers as to why this happens. Now, thinking about those curiosities, again, that core, that's about 16,000 Kelvin, and then you get out to that chromosphere or photosphere at 6,000 Kelvin, and then out to the corona at 1 million. So why are we walking away from that heat source and actually getting warmer? So we've had hints and glimmers of this before. Parker Solar Probe, an AIA image on the left, and this is the wave action, where you have magnetic fields that are represented by the two funnels up top, and they are rooted deeply in the surface of the sun. But the surface of the sun is circulating and churning and moving, and so as that happens, they are rubbing, and so are they creating heat? And creating the energy available to heat to 1 million degrees. And you see here some things that look like they're rubbing, they're definitely twisting and turning next to each other. So again, maybe we've had hints of this before, but with Parker, we can go closer and get a little more information. Another way that we think that things get heated is magnetic reconnection. So magnetic reconnection, again, is magnetic fields bumping into each other, pressing against each other, and then reorganizing and shifting their foot points. So they're anchors into the solar surface, surface. I use surface lightly, but into is anchored, and they reorganize, and that's a huge explosion here of energy that then could be released for heating. And we again have images that show us this reconnection that go along these lines and these bright lights that's heating that area locally. So we use all of our assets in the Heliophysics Observatory in order to better understand this coronal heating. So as we get there, Parker took off from Earth, went closer by doing a Venus assist. And we actually do 7 Venus gravity assists, where Venus flings us in a little closer to the sun. So she takes some of our angular momentum and changes our direction towards closer and closer towards the sun. And as you see, the orbits that are in red gets kind of tighter and tighter around the sun until our last orbit, or our orbit that's coming up in November, where we pass and we get to that 9.86 solar radii. We're not able to get any closer. Believe me, we tried. We tried to figure out a way to end in the sun, but it's surprisingly hard to give up that angular momentum. So once we get there, we needed some measurements. So this was an early model that we built of the spacecraft at a restaurant, at a science meeting. And we figured, again, we needed to measure the temperature because that seems to be important. We need some type of weather vane because we keep talking about wind, magnetic field, so some type of magnetometer, as well as a camera because, again, any good trip, we should have some pictures. So what I'm going to talk about now is that basically the wind vane, the solar wind electrons, alphas, and protons, which is the solar probe cup, which again peaks across the previous little cup, peaks around the heat shield, and the solar probe analyzer, the B, which is the behind, and the analyzer A, which is both ions and electrons, and that is ahead, or the way the spacecraft is actually heading. And what we measure goes back again to those plots I was showing, the crossbars with the contours. So it's velocity distribution functions, and all that means is that we determine the number of particles versus a certain speed or energy. And so we count particles for each energy, and we kind of step through them and then come back and step through them and step through them very, very quickly in order to tell what is going on in the wind. And we get the velocity by taking the center or the peak of that distribution of particles, and then adding them all up is the density that we have sampled there. And the width of this, or the spread, is actually the temperature. So that's how we are able to do that. We're able to do that for hydrogen as well as helium, because although hydrogen makes up the most of the solar wind, helium is also a good indicator of how other things might react in the solar wind, as well as it does carry a lot of the energy around. So this is an image of the solar probe cup aboard Parker Solar Probe as it was in final development. It is really a work of art, and still looking at this, things that I'm looking at are this inner cup. So this is where the particles would flow in. This is a heat shield, the silvery, it's not silver, but silver colored heat shield to keep the heat off of the cup. Particles would go through this fine mesh and in through this aperture down here and be counted on a charged plate. There's some high voltage back here that runs down it to operate that sieve to count to step up in energy and see what can make it through. And so this is an image of that cup. And this cup has been used in many different ways. It's also sometimes called a retarding potential analyzer. It was on Voyager. It was on the WIND spacecraft. It has been used in many different applications. And the standard was kind of to use aluminum, but at these temperatures, which is greater than 1300 C, you really can't use aluminum. It will melt. So instead, we had to use tungsten, molybdenum, niobium, titanium, and sapphire. So this is a really specialized cup. There was a lot of materials development, which was really interesting, and learning the characteristics of certain things. Right here in the close-up, that's actually where the sapphire is. So when we were first talking about this cup, there was talk of having the sapphire standoffs like that we have there. There was something about rubies. I was all about this cup. I thought this was going to be the best bejeweled cup ever. Now, again, that's lab-grown sapphire that is used there. So it's a little bit different than the blue that we're used to in jewelry. But again, an ingenious use of materials. So this cup, also another thing that we would use would be epoxy to keep things together, especially during launch. You don't want these any screws to shake loose. So you put a little bit of epoxy in there, set it, and make sure that it doesn't fall out. So instead, I hope you can see the fine detail here that where they had to use safety wire through these I think they're actually double-aught screws, and make sure that everything stayed safe. So this was, working on the smallest details in order to keep it safe to get it all the way to the sun. Since we were going to the sun, we also needed to test it sufficiently, but normal test facilities are insufficient because they might have a particle detector or a little bit of heat or cold, but not the temperatures and the flux that we were looking for. So again, with the ingenious and innovative ways to look at things, the things that have little stovepipes on top of them are actually IMAX film projectors with the lens reversed so that it focuses instead of defocuses the light. It goes through the second set of mirrors and into this chamber where the cup is sitting just outside of view. There's also a particle detector in the tin foil around or aluminum foil around here that delivers radiation to the cup so it can measure it, and so we can test that it actually was working as it should be. Another cool testing photo that I love is the testing of the solar arrays for Parker. So to see that each one works, there was a known wavelength, put into them, known amount of energy, and marched up so that you could see that all of the solar arrays worked perfectly. And again, the bottom where there's more but closer together are those fingertips that just stick out to get us power when we're closest to the sun. And this is where the suite sat on Solar Probe. And the cup is up here. The span A and B are down here. Again, our phone home, our arrays sitting on top of the third stage that made a perfect launch just this time in 2018. So I would be remiss if I did not acknowledge all of the amazing folks that worked on this. I was commenting earlier that at some point in time, it was over 1,000 people working on an aspect of Parker. And on the upper left, you see myself and my colleagues, Tony and Chris, about to integrate SBC onto the spacecraft. There's our launch providers, launch service providers, helpers on an eclipse day. Then all of the scientists that gathered with Eugene Parker, the namesake of this mission at Applied Physics and Lab at Johns Hopkins outside of Baltimore. Really excited to get all of that data. And Gene was really an amazing person. I was so lucky to be able to talk with him and to work with him a little. He was a great man, and he really persevered. One of the reasons why this spacecraft is named after him is he came up with the theory of the solar wind in a paper in 1958. And it's a story of persistence where initially when it was submitted, it was rejected because it went against common knowledge at the time that this did not happen. And so he checked his math, he resubmitted. The editor was finally talked to him and said, all right, can't find anything wrong with it, even though it might not be might not be right, so let's publish it. So this perseverance really allowed him to start to lead the field. And then Marcia Neubauer, who's over here near this in the picture, she was also one of the folks who made the first measurements to start in space that started to show that yes, what he was doing, what he was saying in terms of his theory was correct. There was this constant wind and outflow from the sun. So as PSP again makes this trip to the sun, it goes through multiple regions of the Venusian plasma. So there is solar wind velocity, velocity and magnetic field strength, and these are each of the 7 Parker flybys of Venus. And their trajectory. The first one was kind of shallow, the second one here, and it got really close on number 3, and we are up to 7 or 5, and 7 will be close as well. So at one point in time, I think it was the distance between Boston and Oklahoma, close to Venus. So we became a Venus mission, a little bit of a Venus mission, as well as a solar mission. And this was one of the WHISPER images that was taken of Venus, and you can kind of see a slight glow here, and there is some little atmosphere or around Venus, and this is the WHISPER data on the left, and then actually Magellan data on the right, and looking that you could almost see the masses that you see in the Magellan. The Magellan images is also seen in the WHISPER images. So this was really great to study if there's any changes while we were flying near Venus. And so magnetic switchbacks. So this was one of the first discoveries or rediscoveries. We knew from the Helios spacecraft in the that went almost close, 0.3 AU to the sun, not 0.1, that there were these switchbacks, these magnetics flipping back and forth. So the plot you see on the left, the squiggly lines are that flipping back and forth. The magnetic field goes one way, the other way, one way, the other way, one way, the other way as you're flying through it. There was really a sense of outward propagation. Now, I also will fully realize that this takes a minute to digest, even if you know what they're talking about. And one of the joys of Parker and all of its discovery is that we've really been able to now take a look at this, and this is the visualization that was made using that data and that understanding. So these are the magnetic switchbacks, these S shapes that you're seeing come off the sun. So what I really love about this mission, and again, folks being interested in it and the great folks who work on it are able to take that data and show you what it looks like in a visualization so you can start to understand it, because you don't necessarily need to know every bump and wiggle, but you need to start saying, oh, when it comes off the sun, it's not necessarily just a straight line, that it's much more complicated. It's not just those outflows, but there's waves in the outflows as they go out. So that's, again, one of the early Parker results. And now a flyby, or a simulation of a flyby of Parker going towards that wavy surface and actually crossing the Alphane point. So realizing that the Alphane point is actually an Alphane surface, and it's wavy and bumpy. And that's partially because of magnetic switchbacks. It's partially just because of pressure balances, things like that. So this is the sun with its outflow. And again, the visualization of looking at inside of what this looks inside versus what it looks outside. So I could show you those squiggly line plots, or I can show you these beautiful animations. And, I personally think they go well together to kind of see, okay, yes, this is an area where it's slower. This is an area where the speed is faster. This is a more ordered place. This is a less ordered place or more chaotic place. And that's really important as we move forward. So Parker did not intend to study dust, but during its first few orbits, it did get some dust measurements and was able to look around and actually figure out some flux from the dust, as well as to model the dust that is around the sun. And initially, I did not think dust was that interesting because it's what I try to keep out of my house. I spend a lot of time dusting some weekends, but it really tells the story of our solar system and any solar system and the evolution of those solar systems. So it really is important to be able to study it and to be able to quantify it since we're that close. Since the solar system formed out of a dust cloud, it's really important to understand what's left because that tells us how the evolution happened. So there's current results as well, more recent observations that show that we are now being able to fly through and to look inside from inside the ring of dust that's left, as well as from outside, since we can fly through it with Parker. So there's much more to be understood there, and much more to contribute to other parts of astronomy. So we're able to use this information for exoplanets and other stellar systems. So again, the dust grains collide, and there are some beta meteorites that escape the solar system due to the pressure of sunlight, which is amazing to me that the sunlight can just press them out, or press them outward when you're that close to them. Now, WHISPER being able to fly through this, and Parker Solar Probe being able to fly through this, has been able to start to map those little meteoroids as they go out, and so these streams collide with grains of dust, and they're eroding the stream and really doing a spray basically in a certain direction. Since you're running into something dense, you can throw off more particles. Again, WHISPER is able to pick all these up and be able to plot them, and we're getting a better picture of what that dust cloud and what stream interactions from other orbiting bodies in the solar system do. So this is really an interesting place to study. Again, WHISPER and the dust was looking at dust trails from comets. So we were able to study comets as well as the sun. So it's not just about the sun and all the coronal mass ejections that I love. And this is just, again, looking at where the comet goes, where the Earth is, and then where PSP is the dotted line, and the sun is in the center. So we were able to make those measurements there. Taking pictures of other comets and dust tails and understanding them. And then near and dear to my heart, coronal mass ejection. So Stereo was looking at the sun, and if you play this video, you might be able to see what you might think is a coronal mass ejection, maybe if you kind of squint and turn sideways. And but then what we do is we actually take a difference of these movies and subtract one frame from the other so that we can see the differences. And you start to see that there's actually a large coronal mass ejection at that same time. So this is the same time frame, just we've subtracted them so we can actually get a picture of what's happening. And it just happens that Parker was flying through that. And that was our first encounter. We had initially predicted, when we were doing our calculations, because we were only on 1/10 of the time that we actually are on now, we would only see maybe one coronal mass ejection in the 7 years of a prime mission. We ended up seeing 2 in the first revolution, or first orbit. So we knew we were in for more and more surprises. And this is considered a stealth CME, or again, you couldn't really see it in other ways. And how you tell this is a CME is this temperature drop. So a density kind of increase over here, velocity, and then a twist in the magnetic field because it's twisted off and pulled along. So that is our coronal mass ejection in the sweep and fields data. There's also clues to stellar angular momentum loss. So again, such a treasure trove from probe that we get with all the data. So there was measurements of, again, helium, or the alpha alpha particles. And what these beautiful plots show is how much angular momentum is found in these. And so these weird loop shapes are what the orbit of a probe looks like projected into this frame of reference. And it will tell you what's carrying along or around the magnetic, angular momentum flux. And it's actually the alphas. And so that means that alphas are important for actually breaking of a star or slowing down the spin. So this is really interesting in terms of stellar evolution, not just the evolution of our star. So what's next for Parker? Venus flyby number 7. So we're getting a little bit closer each time. And this is actually the last time we'll encounter Venus on November 6, 2024. She will break her own speed and distance record. And the closest approach will be on December 24th, 2024. So quite the Christmas Eve. And as Parker takes its final approach and will be able to continue going around the sun and orbiting and showing us all of these with its white hot touches on the front, we're ending the heliophysics big year in a big way, and we're really embracing all that's new and not really ending the big year, but starting a new one. Now that we've been inside the corona or in the Alphane point, we are really looking to going back and characterizing it more. We are always more questions than answers sometimes, and looking forward to a bright future with many missions, other missions, going to be launched in the next year for heliophysics, which gives us more tools to study this, from the EASY mission, which will study the Earth's atmosphere and its response to the solar drivers, as well as the Punch mission, which will look at the sun and be another piece of the puzzle with probes measurements. We have also Carruthers and IMAP launching next year. So just such an exciting time to be a heliophysicist and to really appreciate all that hard work it took to get closest to the sun. Thank you, and I'm happy to take any questions now.
Great, this is really great, Kelly. And we do have a few questions, and some of them you might have touched on during your talk, but let's get to them. And so Chanel asked that he'd love to learn more about the engineering advances that allowed a space probe to get so close to an active star. And you alluded to this, but maybe you could elaborate a little bit. How are the instruments and observatory protected from the intense heat and EM radiation?
Great question. Yes, there were definitely advances in terms of being able to have that carbon-carbon foam that, again, protects us from most of the sunlight. Things like the probe cup that sticks around the side. There was a lot of looking into, again, materials that we normally don't use. We tend to stick with aluminum, things that we know how to machine and utilize well. So we had to look at things like titanium and rubidium and things that we just weren't used to using. So that was part of the technology revolution. The other thing was the change in the mission trajectory. So there were earlier thoughts about Parker Solar Probe, and it would have been a one-shot mission. You would have gone straight into the sun, and you'd have one chance to do the measurements, and it would burn up. Instead, there was a great woman at APL who recognized that you could do this Venus encounter and slowly walk your way down into the hot corona, and that would allow you to dissipate heat as you're flying around, and it really was the way to get there and to get much more data. So it's much more satisfying, and we're able to get multiple samples instead of just a one-shot test. The other thing about it is that although we're going to some place that is 1,000,000 degrees, it's really undense. So it's kind of like the difference between if a hot plate, you touch a hot plate at 100 degrees, you're probably going to get scalded. Whereas if you're sitting in a sauna at about 110, because the air is diffuse, you don't feel it, or you don't actually get burned. You might feel a little hot, but you won't feel burned. And that's the same thing that happens with all the materials there, is that we're going fast. It takes a while, since there's none of that thermal conduction or the actual touching of other warm molecules to warm you up, that it actually stays relatively cool 1,300 degrees. So there is a couple of advances in there, as well as some ingenious kind of sneaking in and sneaking out to get us to the right temperatures.
Great, thank you. I'd never quite thought of the sauna model for orbiting around the sun. So that's a good one. I like that.
Yeah, definitely.
So James asked, are the high node jets the same as spicules?
Not just the same as spicules. These are X-ray jets that are much that protrude from the sun, versus the spicules, which are seen in the photosphere, chromosphere. The spicules are in the chromosphere, so they are different. So the jets are releasing material, and the spicules are kind of dancing around on the surface.
Okay, great, thank you. And then Teresa was wondering, are the sweep measurements continuous or distinct? Are they single times, or are they over a long period of time?
Right. So that's a great question, because initially we were designing for a 10-day encounter. So we would go in close, turn on for 10 days, shut off to conserve energy, and then repeat as we did 25 times. We were lucky to actually be able to be turned on most of the time, except when we're phoning home. That Ka-band antenna takes a lot of energy, and you have to point it in a certain direction. So we made sure to, we need to kind of not take measurements at that point in time. So they're pretty continuous, with like bands for when we're communicating with it, we can't be taking data.
Okay, great, thank you. Lauren asks, what's the general explanation for the temperature drop within a CME? And she is relating this to the data from the PSP 2018 fly-through.
Yeah, definitely. So the temperature drop is due to the fact of what you're bringing along with you. So when that twisted structure twists up, it's pulling stuff below it that's cooler up with it. And when it's released, it keeps that cold stuff in the middle, or cooler stuff in the middle. And so as you go by, you would see something that was warm, and then something's cool, and then something that's kind of warm again. So that cooling off is due to the stuff that's been dredged up and taken away with a CME.
And then Art asks, what have the Parker Solar Probe's observations revealed about the role of magnetic reconnection events in the sun's corona, particularly in relation to the formation and dynamics of coronal mass ejections, and how might these findings impact our understanding of space weather forecasting?
Wow, that's a big question. So in terms of magnetic reconnection, Parker has seen that in situ. So we're not necessarily looking at the surface of the sun. We're looking at things that were already there, and we've been able to see the exhaust, or the release of jets from magnetic reconnection in the Parker data. And being able to study these for a longer amount of time, it's great to be able to see again that energy budget, how many of these are actually happening. I am not aware right now of a paper that does that, but that does not mean it's not out there. I should go home and do my literature search and make sure that I'm not missing anybody. But again, this magnetic reconnection and this energization of particles is really key to space weather. So there are people looking at it, and I will search the literature and see what I can find for tomorrow.
Great, thank you. And we have another question. This is a little bit more general question, but one that a lot of times, especially people that are doing outreach, would be curious about. Just how far out into space does the sun's corona go?
Great question. So there is a little bit of debate. But what I tend to classify is that the corona goes out to the Alphane point. And so that's everything inside of that point is magnetically dominated by the sun. So it's controlled by the sun's magnetic field inside of that. Outside of that, the wind is driven outward. So I would consider that the outer atmosphere, and the corona is everything kind of inside of the Alphane point.
Okay.
Or Alphane surface.
Great.
And this will be the last question for the evening. And you alluded to going up and having the last close approach in December. But what happens after? And I know that at some point it's going to be deorbited into the sun. And so what's going to happen after that?
Great. Yeah. Parker has we'll go in this time, and we'll have, I think, 2 more orbits before September of 25. And at September 25, we go through a review process to make sure that that everything's still a go. We've still got fuel. We still have meaningful science to do. We're taking good data. We do that review. And it can then continue as long as there is fuel aboard, because you got to keep that Parker Solar Probe front shield pointed directly towards the sun. If it tilts one way or the other, the things behind it will burn up. So we want to make sure to have fuel to make those small adjustments. When that fuel runs out, or when it becomes decommissioned, what will happen is it will end up turning, and it will burn up, and it'll be a rock that will kind of orbit in that specific orbit for the rest of time, until the sun becomes a red giant. It won't go into the sun, and we again tried to figure it out, but it's actually a surprising amount of change that you need to make in the angular momentum. And if you don't have any fuel left, you can't do that, and we don't have a Venus assist to do that. So we will end up just kind of stable in that orbit as a little rock at the end.
Okay. It's not like all the satellites that are going around Earth that are running anything, that we'd like to figure out how to deorbit them all so that we don't run into them with the ISS. So it's okay.
Yes.
So we'll have a perpetual Parker Solar Probe rock orbiting the sun. So
orbiting the sun, yes.
An artifact, you might say.
Yes.
Well, thank you so much, Kelly. This is absolutely fantastic. This is a wonderful talk. And I looked it up. You spoke to the Night Sky Network in August of 2022. So it was almost exactly 2 years ago. So that was so it's good to get this update. And we'll have to ask you back here in another year or so after we get the final orbit and find out what's going to happen. After you have that review panel, we'll have to see, what's going to happen. So, all right. Well, thank you everyone for being here. And we've got 2 more days of meetings. And Greg, do you have any words for us for anything else? Then I have one other thing after Greg.
Just stay tuned. We might make an additional session on Saturday. There is a vacant session that we may add a talk or 2 into. So stay tuned for that. But otherwise, we'll see folks in the morning, Pacific time at least. So look forward to the next 2 days.
And make sure you come back for tomorrow evening's session at the same time at 5:30. We will have basically the star and the filmmaker for Small Town Universe. And we will also have a special visit from Jill Tarter, who will introduce the film. So we're very much looking forward to that. So join us tomorrow, and have a great evening, and take care, and good night.
Thank you, Kelly.
All right, we're out, and good night, everyone. Thank you,
Kelly.
Thanks again, Kelly.
Bye. Thanks.
Bye. And Kat,